let's start out by just illustrating Mr. Palmer driving in his Toyota Sienna minivan, year 2000, burgundy. Anybody remember what's on the left-hand side? A dent caused by what? A tree that ran out and hit the car when I was driving. So here I am. Velocity of Mr. Palmer is 70 miles per hour. Now, up until this point, every velocity, every speed, everything we've talked about has always been relative to the Earth. But now we have to start specifying what it's relative to. So this one is going to be the velocity of Mr. Palmer relative to the Earth. So it's what we're used to. This is just the velocity of Mr. Palmer relative to the Earth. We're going to have Donahoe. Oh, I have a hard time with your name. I'm sorry. Donahoe is going to be driving a convertible. Woo! The velocity of Donahoe with respect to the Earth is going to be an unrespectable 90 miles per hour. Now, here's the question. What is the velocity of Donahoe with respect to Mr. Palmer? In other words, when Mr. Palmer looks out his window and gives a to Donahoe for driving too quickly, Emily C, that's what I'll call you, easier. For driving too quickly, how fast is she moving relative to me, please? Matt?
160 miles per hour.
No, it's okay. We're both moving to the right. I think you might have missed that, Eric.
20 miles an hour?
20 miles an hour, because we're both moving to the right.
Yeah.
So I tried to illustrate that in the figures. I know they're not the best pictures. So the velocity of Donahoe with respect to Mr. Palmer is going to be the velocity of Donahoe with respect to the Earth minus the velocity of Mr. Palmer with respect to the Earth, or 90 minus 70, which is 20 miles per hour. Okay. What then is the velocity of Mr. Palmer with respect to Emily C? In other words, when Emily looks out her window and goes, "Oh, Mr. Palmer," how fast am I moving relative to her?
Negative 20 miles per hour.
Negative 20 miles per hour. In other words, if Emily C takes herself to be the center of the universe, it will appear as though I am moving backwards relative to her at 20 miles per hour. The basic concept of relative motion. Different example. We're going to pretend that you are stationary observers sitting in your desks in a nice, lovely field next to some train tracks. So you are stationary observers in your desks. On the train tracks, there will be a train that will be constantly moving to your right at 5 miles per hour. So the train is always moving to your right at 5 miles per hour, and I'm always standing on that train. And we're going to talk about what happens when I throw the tennis ball at 5 miles per hour. Now, the train is moving to your right at 5 miles per hour. I'm going to throw the tennis ball to your right at 5 miles per hour. What is the velocity of the tennis ball with respect to you? Sicarelli. Here, so the train is moving to your right at 5 miles per hour, and I'm going to throw the tennis ball to the right at 5 miles per hour, and I'm standing on the train. No, that's okay. You're misunderstanding. Nate?
5 miles per hour.
No, also not 5 miles per hour. We'll get there eventually. Who?
10 miles per hour.
10 miles per hour, because I'm traveling this fast at 5 miles per hour, plus I throw the tennis ball in the same direction, so you're going to add the two. You're going to get 10 miles per hour. Now, I'm the stationary observer on the train, or I'm sorry, I'm on the train, you're the stationary observer, and I throw the tennis ball again with the same 5 miles per hour to your right. How fast is that tennis ball moving relative to me? Eric?
5 miles.
5 miles per hour. What about this? If I'm standing on the train that's moving this direction at 5 miles per hour, and I throw the tennis ball up and I catch it, so we're going to do that again. I'm moving on the train this direction at 5 miles per hour, and I throw the tennis ball up and I catch it. What is the path? What's the shape of the path as described by you, the stationary observer? Duval.
The path of the ball.
The path of the ball. Just describe the shape of the path.
Like that.
What's
like
it called?
A parabola.
A parabola. It's going to follow a parabola, right? I throw it up here, it comes back down here. What is the shape of the path relative to me, Mr. Palmer? What do I see the tennis ball do? Thomas.
Straight line.
It's going to go straight up and down because to me, I'm moving with the tennis ball, so the tennis ball is just going to appear to go straight up and down. So notice how the description of how the tennis ball moves is dependent on who's watching it. Let's do something slightly different. So the train is still moving to your right at 5 miles per hour. I'm going to take the tennis ball and I'm going to throw it to the left at 5 miles per hour. What is going to be the speed of the tennis ball relative to you, the stationary observer? Ian?
0.
0. This is just like when I was walking in the opposite direction on the people mover, right? If the train is moving to the right at 5 miles per hour and I throw it to the left at 5 miles per hour, it's going to have an initial velocity of 0. What does that velocity, that initial velocity, look like to me, the person on the train? Adam?
I would say.
Right. It's going to follow a path that looks like this relative to me. What does the path of the ball look like to you, the stationary observer, when I throw it to the left at 5 miles per hour if the train is moving to the right at 5 miles per hour? Adam again.
It will drop straight down.
It will appear as though I have simply dropped it and it will move straight down relative to you. That's what it will look like. So again, the whole point here is that the motion of the ball is dependent on how the person who's observing it is moving.